Hi guys, I'm just gonna state a theorem here. I'm gonna minimize the presentation, the introduction as much as possible, um, because if I start talking about moduli spaces of principally polarized abelian varieties or abelian varieties um, uh, in their representability as spaces, algebraic spaces, stacks, and things like this, or formal spaces, and how formal spaces completions of these things are related to each other, we get in a big mess. Because it, to do that, I mean, maybe I should have made a video before that, but then this would take forever and we'd never get through this. So I'm going to state this theorem first. So let me about the tangent space. So this is going to be about the tangent space of the moduli space of principally polarized abelian varieties and what it looks like. And I want to do this to talk about the Torelli theorem. In particular, the infinitesimal Torelli theorem. So like the tangent map of the Torelli theorem. If you don't know what the Torelli map is, it doesn't matter. Let me just give you the setup here. So we have a ring, we have a abelian scheme over the ring. So these are always smooth. And then we're going to have the dual numbers. I'm writing the dual numbers like this as a functor again because I have the idea of replacing this later with other ring schemes. And then I'm going to take a line bundle in here. So the idea of the line bundle is it's going to induce a polarization from, so this induces a map from A to its dual. And maybe I'll talk about these things. Again, I'm trying to minimize introduction. Maybe I'll talk about these things in another video about abelian schemes. Okay, so so let me just state it. So here I'm not. So this functor here is or so this is here is a category of so normally we have a category of deformations of abelian varieties and line bundles. Over a ring R up to the dual numbers, okay, up to isomorphism. So sometimes we think of this as a category. Right now I'm going to think of this as just like a set up to isomorphism. And what else do I want to say? So the deformations of abelian schemes are they're always going to be smooth. And then, I don't know, okay, let me try and minimize this. So the statement is that this functor, okay, maybe I'll make another video on this. And this goes well. When I talk about this will have to go well with polarizations and these type of things. Okay, basically I wanted to form these pairs. Okay, and so these are deformations. You can see the deformation video, like the one that I gave before, and then I've also done a video on deformations of line bundles. So I hope this is clear, or you have the idea of what it is. If not, let me know. So here we have, so here's the theorem. The theorem says that the deformations of these pairs of line bundle or abelian varieties with line bundles, so these are like polarized abelian varieties. So this is these equicharacteristic deformations where we're just kind of taking these infinitesimals, is isomorphic to a subspace of here. So the idea is that not every deformation with a line bundle is not every deformation, right? So not every like Kadira Spencer guy is going to give you a deformation of a line bundle. That being said, let me say what V of A is. This is the second symmetric space of this. Okay, so H1 of O. All right. Okay, there's other things I could say about this too. I mean, like here, the fact that this thing even sits inside here has to do with something called you want to say the map between functors from the polarization pairs to the actual thing is so-called unramified. So that's like when there exists. So it's like when you have like Étale maps. You have this map, and when it exists, it's unique, right? So it's like this. There's a uniqueness property involved here. Anyway, let me just state the proof. Okay, so Okay, so let's recall. So recall from the obstruction video. So I'm just going to collect some facts. Okay, so recall from the obstruction video. So that we're given some A tilde, which is a deformation of let's say of abelian schemes of A over R to D1. So it's important that this ring be this shape, right? So that we have a Kadeira-Spencer construction. There's a certain obstruction class, okay, of lift to. So we have this line bundle here to lifting this thing. So this thing is equal to 0 if and only if. So there exists some L tilde, a line bundle on A tilde, deforming L. Okay, and so this thing here, this lives in H2 of A of O of A. Okay, so this is what we did, and we actually found out that this guy here was there's another video that I did is I showed that this was the Kadeira-Spencer of the deformation, this infinitesimal deformation, to with this logarithmic derivative of the class associated to the line bundle. Okay, so this one lives in H1 of A, T of A, and this one here lives in, so this one lives in H1 of O, and then when we do the logarithmic derivative, we have, this is A omega 1 of A. Okay, and so these A's here, these are really relative with respect to R, but I'm just simplifying notation. Okay, we can also, we might want to call this class the first Chern class, which is the de Rham version of the Chern class. So this is actually a piece of the Hodge or de Rham cohomology. Okay, so but and that's where this comes from. So this there's some correspondence between these two things. Okay. Anyway, so this obstruction class, so this thing that it needs to be 0 is a cut product of two things, and I proved this in another video. Okay. So yeah. So this is 0 if and only if there's a line bundle here. So then there's extra data. All right. So that being said, let me move on to the next thing. So the idea now is, okay, so what we can do is we can take an abstract deformation in here, right? And we want to kind of characterize this subspace. Okay, we actually know a priori that this deformation functor is going to be a subspace here from a certain condition about these functors being unramified. So we know what to look for, okay? Yeah. So okay, that being said, let me just do some computations. Okay, yeah. Let me just write down some computations. Okay, so this guy here. Okay, it turns out that the tangent bundle of an abelian variety, and in general group schemes, are trivial, right? So this guy looks like smooth group schemes. So we're gonna have them be smooth. So here, this looks like this. Okay, so it's really, this is the Lie algebra, the tangent space at the identity here, tensored with OA, and so this is like a free module, right? So we can bring this out, and this becomes, and let me say this, there's a map here, it's an isomorphism, so this tensored with T of AE, okay? The tensor product's over the base, okay? And so if we wanted to change this for a scheme, we would have to do these direct image things. All right, so we have that guy. Another fact is that this guy here, this is the tangent bundle, so this piece here. So this is actually the tangent space of the dual. So I haven't proved this in the video, but this is a fact, okay, that the tangent space of the dual abelian variety, so this is actually the Picard of A, pick 0 of A, that this is equal to the tangent space of the identity, okay, so of the dual abelian variety. All right. Okay, so we have this guy here. So that means that this guy here is really isomorphic to, well, T of a T, E, tensor T of AE. Okay, so we have this whole thing here. Okay, now I'm going to use this information to kind of construct a diagram that's useful. Okay, so the diagram that I want to construct is the following. So we have H1 of A, T of A. Okay, and this chain of maps here gives me this map here from ATE, a map like so. Okay, and this is an isomorphism. Okay, we also had this obstruction class thing, so I can take this and I can cut product with this the cut product with this class. So here we'll have the Kadeira-Spencer class, and this is the deformation class that characterizes this A tilde, and this goes to H2 of A O. Okay, and this is where the obstruction class lives. So if I take the Kadeira-Spencer class here, then I get this obstruction to lifting the line bundle. This map depends on the line bundle here. Okay, so let me give you another fact about abelian schemes. So its cohomology, so like H2 of A of O of A, is actually the second wedge product, like so. Of H1 of A of O of A. So we have an isomorphism like this. This is in like Mumford's abelian varieties. So this is something that we have. Okay, so we have a map here. Okay, and here we have. So this is let's say the second wedge power of H1 of A O of A. Okay, and this is also an isomorphism. Okay, so we have this kind of commutative diagram here. It turns out that here, okay, I'm going to have a map here, F, and I want to describe this map for you. Okay, so here we're going to start with T of AT to E, and then we have this guy, T of A, E. And what we can do is, so we had this, so like I said, that if you're given a line bundle, right, so maybe here's another thing. So given a line bundle on an abelian variety, you get a map lambda, or lambda sub L, okay? And this is a map from A to A of T. And so you can actually get this map, let's say at the identity, from the tangent space of the identity here to the tangent space of the identity here. Okay, so if we apply, well, we just keep this factor the same and then we apply this. Okay, what we get is two copies here. The tangent space, the Lie algebra of the dual abelian variety. Okay, and so now the map here, now it seems to be obvious. So here we're going to go to the, so we're going to go to, we're going to use the isomorphism twice, right? So this is so this is the second wedge power here. Okay, so what we really have is this thing here. Let's write it. Maybe we'll go down here. This guy goes to the second wedge power of T of A T E. Okay, and then we go here. So there's a factorization through this, and this map here is the second wedge power of. Okay, let's call this isomorphism alpha, and it depends on A. Okay, so this is the. Let's actually do it this way. Sorry, let's do it this way. Okay, so we're going this way. Okay, so this is going to be the second wedge power of alpha of A, like so. Okay, and so this whole composition here, this is F. This is this map F here. Okay, so we did this thing associated to the line bundle, so this is also associated to the line bundle, and I claim that this diagram commutes. Okay, so this diagram commutes, okay, and we can use this to now see what the obstruction looks like when it vanishes. Okay, so now we'll look here. So what do we have? Okay, so now here we have, okay, so we have this isomorphism here. So this thing is really, okay, so now I want to prove the claim. It's pretty clear from here now, I think. Okay, so from here, what do we have? So we have that, so we wanted the obstruction class of A tilde over A of L to be equal to 0. Okay, so that means that the composition, so here, when we took our A tilde, or the Canard-Spencer class of A tilde here, we get the obstruction class, and then here, so this is an isomorphism, it needs to be 0 in here. Okay, so we actually, from here to here, let's say from, so we already had the isomorphism here, and from here to here, we had, two copies of the cotangent bundle. So we're actually going to have a certain subspace of the cotangent bundle where the map here is 0. Okay, so we need the map from here to here to be 0. Okay, so it turns out that that V of A, this thing, is equal to the space, the kernel of the map from T of AT, E tensor T of ATE to the second wedge power of T of ATE. Okay, well, this thing is just the symmetric powers. So this is isomorphic to this, and so this is equal to, or maybe equal to, if you want to actually take the definition to be that. And then this is isomorphic to H, so the second symmetric power of H1 of A of OA. Okay, so that's all I really wanted to say. Thanks for watching. Hopefully I'll explain some of these details in another video.